All right, welcome. Today we're going to crack the code on a classic programming challenge. One of those problems that's just a fantastic workout for your brain. We're talking about the foursome problem. We'll break down its super elegant solution step by step, and you'll see how a really tricky problem can be boiled down to something surprisingly simple and quick. So here's the game plan for this explainer. We'll kick things off by figuring out what the foursome challenge even is. Then we'll get to the secret sauce that makes it all work. After that, we'll walk through the main algorithm, talk about handling those pesky duplicates, and wrap up by looking at how well it actually performs. Okay, let's get right into it. Part 1, the foursome challenge. Before we can cook up a solution, we have to know exactly what the recipe is asking for. At its heart, it's really a search mission. You get a list of numbers, right? And a target number. Your job is to dig through that list and find every single unique group of 4 numbers that adds up perfectly to that target. We call these little groups quadruplets. Let's make this super clear with a quick example. Imagine your array is 10, 20, 30, 40, 50, and you're aiming for a target of 100. Well, there's only one way to do it. 10 plus 20 plus 30 plus 40. That equals 100. Boom, that's the quadruplet we're hunting for. Okay, so here's the deal. You could just, check every single possible group of 4 numbers, but if your list is even kind of big, that would take forever. Seriously, we call that the brute force method, and it's just way, way too slow. We've got to find a smarter way in. And that really is the million-dollar question, isn't it? How do we build something that's actually efficient? How do we find all the right answers without our computer getting stuck in a loop for days? And here it is, the aha moment. This is the secret. We don't try to find all 4 numbers in one go. Nope, we simplify things. We lock in our first number, then we lock in a second number, and suddenly the problem becomes way easier. Now we just need to find 2 numbers that add up to whatever's left. We just turned a hard foursome problem into a bunch of easy twosome problems. All right, now let's see how this idea actually comes to life. This is where we get into the nuts and bolts, the core of the algorithm, which has this kind of cool name, the 2-pointer dance. The whole thing really boils down to these 4 steps. First, and you can't skip this, we sort the array. That sets the stage for everything. Then we start looping. We fix our first number, let's call it I, then we fix our second, j. And for every single one of those pairs, we unleash our 2 pointers to search the rest of the array super efficiently. So get this picture in your head. The array is sorted, smallest to largest. We've picked our I and j. Then we drop a left pointer right after j and a right pointer at the very, very end of the array. These 2 pointers are now going to walk towards each other, closing the gap as they hunt for our last 2 numbers. And the logic here is just so simple and clean. We add up our 4 numbers, I, j, and whatever left and right are pointing to. If the total is too small, less than our target, what do? Well, we need a bigger number, so we nudge that left pointer 1 spot to the right. Easy. And if the sum is too big, you guessed it, we do the exact opposite. To shrink the total, we move the right pointer 1 step to the left, which grabs a smaller number. And then, when the sum is a perfect match for our target, that's the magic moment. We found one. We write it down, and then we keep the dance going, moving our pointers to see if there are any other solutions hiding in there. So finding a solution is great, but remember, the problem asks for unique quadruplets. This is a huge detail. We have to be really careful not to report the exact same set of 4 numbers over and over again. And our algorithm has this awesome 4-layer defense system against duplicates. At every single stage, when we pick I, when we pick j, and even after we find a perfect match with left and right, we have these little checks that say, hey, have we seen this number before? If so, just skip it. And this slide, this is literally the code that does it. This is the first layer of protection. It just says, hey, if we're not at the very start and the current number we're looking at for I is the same as the last one we just checked, don't bother. Just continue to the next one. This one line saves us from redoing a ton of work. All right, let's zoom out and look at the big picture. How fast is this thing really? And what happens if we throw some weird or tricky inputs at it? Does it break? So what's the report card on performance? Well, the technical term is n cubed, or n cubed. What does that even mean? It basically comes from our 3 nested loops, one for I, another for j, and then that 2-pointer dance counts as the third. Now, n cubed isn't exactly lightning fast, but compared to the brute force way, oh, it's a massive improvement.
And this is where the algorithm really shines. It's so robust. Given an array with only 3 numbers, it knows it can't find 4, so it just returns an empty list. Perfect. Give it an array that's nothing but the number 2 and a target of 8. Our duplicate skipping logic is so smart, it finds the solution 2, 2, 2, 2 exactly once, not a million times. It handles all these tricky edge cases perfectly.
So, you see, what we've really learned here is more than just a fix for one problem. It's a whole strategy. Take a big, scary, complex challenge and break it down into a smaller, simpler piece that you already know how to handle. And that kind of leaves you with a question, right? What other puzzles out there are just waiting for you to solve them by breaking them down?